Okay, part 2 of chapter 8, elastic potential energy. A body is elastic if it returns to its original shape after being deformed. Elastic potential energy is the energy stored in an elastic body, like in a spring. Okay, and elastic potential energy stored in an ideal spring is half k x squared, and this is the amount of it. If you want to care for direction, it is, you have to put a negative here. And if you remember why, because F was negative kx for a spring, okay, that was F, and the work was the integral of F dot dx, okay, or the integral of negative kx dot dx, which is negative k, the integral of x dot dx, okay, which is negative k. The integral of x dot dx is half x squared. So I can write the work being negative k, half k x squared. Okay, this negative, the only meaning that this negative has is that it means that you are having a force that is in the negative direction of displacement. Okay, in other words, if you stretch a force from its normal or unstretched position, okay, kind of like that, there you're storing a force inside this spring, which is in the opposite direction. It wants to put it back. It wants to go back to its original shape, okay, but the displacement is in this direction, so this is your displacement. And this f of negative kx, this negative means that they are in the opposite direction. So this negative here means that they are in the opposite direction. Okay, so work of the spring is, the amount of it is half kx squared, which is u initial minus u final, okay, or negative delta y, in other words. Okay, so this is negative delta y, or sorry, negative delta u, not y, negative delta u of the spring. And if it's initially located at a point which is unstretched, or at the standard position, then it does not have any potential energy stored in it because it's not moving at all. It's just at this relaxed position. So this is 0. And then you have negative u of f equals half kx squared. Or in other words, you have u of f final being negative half kx squared, which is the same thing that we talked about over and over and over right here. All right. So and this is from this part of the video on, this is the part that we're going to combine everything. So conservation of mechanical energy. Definition of mechanical energy is very easy. Whatever potential energy you have plus whatever kinetic energy you have, this will give you, this amount will be your total mechanical energy. So potential energy plus kinetic energy will give you mechanical energy. So have that in mind. If you don't have a non-conservative force, okay, if you don't have, for example, friction, if you don't have air resistance, if those are absent from your situation or from the problem that you're solving, then final and initial mechanical energy should be the same. Or in other words, E is constant. They can change to one another, okay? So for example, if you have E being K plus U, if potential energy increases, then your kinetic energy will decrease to keep this E as a constant value. Okay, in other words, if you're looking at this, I have a person here, and he is jumping up. In other words, he is gaining potential energy because it's going up. So remember, the potential energy was mgh. Okay, so he's going up. This h is increasing, so he's gaining some potential energy. If I want the E to be a constant value, if U is going up, then K has to drop. So when he's going all the way up here, he's losing some velocity. He's losing some kinetic energy. So K decreases, U increases, but the value of K plus U will be the same. Why is that? Because there is no non-conservative force in our problem. We do not have air resistance. We think we do not have air resistance. We do not have any friction with the surface. So if that's the case, then you have this mechanical energy always being conserved. So the total mechanical energy of a system is the sum of its kinetic energy and potential energy, as I said. A quantity that always has the same value is called conserved quantity. Okay, so just like mechanical energy, which is a conserved quantity, does not change. Okay, when only the force of gravity does work on a system, the total mechanical energy of the system is conserved. This is an example as I was just talking about it. So if all the forces involved in the problem are coming from conservative forces, okay, either a spring moving up or down, and you know what the value for U of the spring is, or the potential energy of the spring is, or if you have an object going up and down, then without any friction, you know what the potential energy of that object is due to gravity, which is mgh, okay, or mg times height. If these are the cases, and you don't have any type of friction, you do not have any type of air resistance, then your E, or total mechanical energy, is conserved. Okay, so let's take a look at this example. This is a very important basic example. So you throw a 0.145 kilogram baseball straight up. Okay, so you're starting from this point. You are sending this baseball all the way up. So the mass of the baseball is 0.145 and the velocity is 20 meters per second. It's going all the way up to this point, which is at some point, but the velocity of that is 0 because it will eventually stop when it goes up. It doesn't go up forever. It's going to stop at some point, right? So we want to know what the height is. So if I want to a little bit make this problem easier, I am starting from this point, from height of 0. So initial height is 0. And I am going all the way up to another point with the height of unknown. So final height is unknown. We don't know what it is. All right. And here the velocity, initial velocity, is 20 meters per second. And here it will eventually stop at some point. So the final velocity, or V2, is 0. Okay. So V final is 0. So if you want to take a look at this problem, do we have any non-conservative force? No. We do not have friction. We do not have air resistance. In other words, the total mechanical energy is a constant value. So whatever that you have in point 1, you're going to have in point 2. So which is the point 1? This is point 1. This is point 2. Okay. So if that's the case, then K in point 1 plus U in point 1 should be equal to K in point 2 plus U in point 2. All right. So let's take a look. In point 1, it's on the ground. It's at the 0 level. So it does not have any potential energy. Remember what the potential energy was? If you don't remember, I'm going to write it here. Potential energy was mgh. Kinetic energy was half mv squared. Okay, since you do not have at point 1 any height, so this u is 0. All right. At point 2, you do not have any kinetic energy because it doesn't move. There is no velocity. So this is 0. Or I can say that k in 1 should be u in point 2. What is k? Half mv initial squared, because it's 0.1, equals mgh final. Okay, so this m and this m will cancel out. We're going to cancel it from in both sides. So in other words, giving us this weird number, 0.145 kilogram, it's not necessary because they will cancel out anyway. So I have half v initial squared. I believe it was 20 meters per second. Now I have to square it. G is 9.81 and h of final is unknown. So if I want to solve this, I will have h final. If you solve it for h final, you will have 20 to the power of 2 over 2 times 9.81. Okay, so 20 to the power of 2 is 400. 2 times 9.81 is close to 20, so I'm just going to use 20. So close to 20. And this means that you have about 20 as your final height, 20 meters. All right. So the reason that I said that E was constant is because there was no non-conservative force. Okay. We did not have friction. We did not have air resistance. Okay. All the forces were somehow related to conservative forces like mg that you can see here. Okay. All right. So all right, I want to solve another example real soon that will go over these that we covered in part 1 one more time. So bobsled going down a track. So I have an object here with an initial velocity of 0. Okay, so initially it is at 0, but it has some height associated with it. So I have a height initially for this object. So there is a height. In other words, at this point, it does not have kinetic energy. So in point 1, okay, the kinetic energy is 0 because of velocity being 0. But the potential energy is non-zero. Okay, and it is equal to mgh. It is not 0. It has a value associated with it because there is height here. So if you calculate that, and kinetic energy is 0, obviously, potential energy ended up being this much, 600,000 joules. So that means if I add these two, I will get the mechanical energy being 600,000 joules, okay? If there is no air resistance and there is no friction involved, then this value would be the same for each point along this path, because we do not have anything, any non-conservative forces, okay, to reduce this amount of mechanical energy for us. So at point 2, I would have 200,000 joules of kinetic energy, and I have 400,000 joules of potential energy. But if you add them up, you will get the same value that you had in point 1. It is the same thing for point 3. It is the same thing for point 4. However, in point 4, once you're on the ground, the h is 0. So on point 4, H is 0, and therefore the potential energy for point 4 is 0 because there is no H, so mgh is 0. So all the force, the energy has turned to kinetic energy. So now that 600,000 joules is all turned to kinetic energy, but the value of mechanical energy or total energy is conserved. See, for point 1 it is 600,000. For point 2 is the same, point 3 is the same, point 4 is the same. Okay, so it does not change. Okay, let's take a look at this example. So I have a gymnast leaving a trampoline at an initial height of 1.2 meters. So initially, I have a height of 1.2 meters, okay? So this is what the height is initially at this point from the ground. And then it will go and reach the maximum height of 4.8 meters before falling down. So it will go all the way, okay, 4.8 meters up all the way. So that's my point 2. So this is point 2 and this is point 1. All right. This point is point 1 and this point is point 2 for me. Okay. Now, what was the initial speed of the gymnast? Okay. So do we have any forces that are non-conserved? Do we have any friction? Do we have any air resistance? We do not have any information about those, so we assume that they are 0. So we can write, since there is no friction, we can write that total mechanical energy in point 1 should be equal to total mechanical energy in point 2. Total mechanical energy in point 1 is K plus U. Total mechanical energy in point 2 is K plus U. Okay, just pay attention to these indexes that I am using. So for point 1, I am using 1, and for point 2, I'm using 2. This is K, by the way. Okay, so K of point 1 is half M V of point 1 squared plus U of point 1 is M G H of point 1 equals. On point 2, once it's going all the way up, he will stop at some point. Okay, so the final velocity of that point is 0 because he's just stopped. He's not going any further up. So this is 0, but you have potential. So mgh2. If I factor out m from left-hand side, I can cancel that with this m from the right-hand side. In other words, I can cancel out this m from either side. And then what I have is I have half v1 squared plus g h1 equals g h2. Okay, let's bring this g h1 to the other side of the equation. Okay, so I have half v1 squared equals gh2 minus gh1, or I have half v1 squared. I'm going to factor out g here, gh2 minus h1. Okay, so I have half v1 squared equals g, which is just g. h2 minus h1. 4.8 is h2. 1.2 is h1. So 4.8 minus 1.2. Okay, 4.8 minus 1.2. And we have a value for G, so let's substitute the value that it has. We know what G is. 9.81 it is. 9.81. So V1 squared is 2 times 9.81 times 4.8 minus 1.2. Okay, or V1 is whatever that I have underneath the square root. So 2, 9.81, 4.8 minus 1.2. And that's your velocity at that point. It is very, very easy to use conservation of energy in the problems, okay? It is very, very, very useful. So when other forces do work, how about that? So the work done by all the forces other than gravitational force equals to the change in the total kinetic energy, okay? In other words, if you remember from working energy theory, we have sigma W, or total work done by all the forces, okay, is delta K, or K2 minus K1. Okay. Now, so this is what we had before. What was what was this one? The work of gravity. You remember what it was? Negative mg delta y. Do you remember this? If you don't remember, I have it right here in the first video. Go ahead and check it out. W of gravity is negative mg delta y. Okay? Negative mg delta y. Right? So I have that. Now, do you remember what U was? U was mgh, or by the way, I can write this as negative mg delta h, right? And y and h, height or along the y direction. And U is mgh, so delta U, which is U2 minus U1, or U final minus U initial. So delta U, which is U final minus U initial, is mgh final minus mgh initial, which is mg h final minus h initial. Okay. Or mg delta h. Okay. All right. So when you're looking at this, when you are looking at this, what is this? Negative mg delta h, positive mg delta h. So I can write this as negative delta U. Okay, so the work done, so important, the work done by gravity is negative delta U. Right? So this is what it means. And that's how you find it. So this is mg delta h, which is delta U, and there's a negative here, so there's negative delta U. So I am going to give this a little bit of attention, which I can, I think, do with doing that. Okay. Now, let's take a look at formula. So I have total work being delta K. If you add all the works of all the forces, it will be change of the kinetic energy. Now, if I want to write down the total work, it will be the work done by gravity plus the work done by the other forces involved. Okay, let's say that the force that you apply on an object, and that is equals to K2 minus K1 or delta K. Now I can write this work done by gravity as this, as I have already proved it here down here. Okay, and then that means this. So work done by other forces plus work done by gravity is delta K, which is K2 minus K1, okay? And I have already, this is all the forces involved in our problem, everything, okay? This is W total. I have already proved for you that the work by gravity is negative delta U, so W of the other forces, negative delta U is delta K. Or work done by other forces, other than gravity, everything else other than gravity is equal to, I can bring this negative delta U to the other side, so I'll have delta K plus delta U. Okay? So giving this guy a little bit more attention of doing this. So I can easily refer to this as the star equation from now on, because this is very important. All right, so how do we solve the problems now? If we have all of this, how do we really solve the problem? So there should be some, you should have some strategy when you are solving the problem. Decide whether the problem should be solved using Newton's laws or the energy conservations, or maybe the combination of both, okay? Look for things, varying forces like, you know, energy or, you know, elapsed time when it comes to Newton's law. For the energy approach, okay, identify initial and final position, draw a sketch, a very simple picture, define a coordinate system, usually plus y is positive, negative y is down, okay, and identify forces that do work but cannot be described by potential energy, and draw a free body diagram for that, okay. List the known and unknown quantities, everything that the problem is giving you, coordinates, velocities, height, time, whatever that's been given, okay? And then try to execute the energy approach and then evaluate your solution to a problem using the other methods that you have. We're gonna go over some of the examples soon. So we have a baseball is thrown from the roof of a 22-meter tall building with initial velocity of magnitude 12 meters per second and directed at the angle of 53.1 degrees above the horizontal. So let me picture the problem for a second. So I have a building, oops. So I have a building kind of like this. So I'm gonna sketch a problem, all right? And then I have a ball or an object thrown out from the roof of the 22-meter tall building. So I know this height is 22 meters. So 22 meters is this. And the magnitude of this initial velocity is 12 meters per second, okay? Now you have a initial angle here, okay? So this initial angle is 53.1 degrees, all right, above the horizontal. What is the speed of the ball just before it strikes the ground? So it will go to this path and a projectile type of path, and then it will hit the ground somewhere down here. We want to know the speed of the ball at this final point, or V final. We want to know what it is, okay? So when you're looking at this problem, you can definitely work this problem from the things that you've learned from the two-dimensional motion and it'll take a little bit of a long time to do it. But when you're looking at this, we do not have any non-conservative forces. We do not have any friction, any air resistance, anything that, the work done by that force will reduce the total mechanical energy. In other words, in point initial and point final, in our case, the total mechanical energy is conserved. Okay, so kinetic energy is conserved. Kinetic energy plus potential energy from initial point should be equal to kinetic energy plus potential energy for the final point. Okay, in the final point, the ball is at the ground. There is no H, so the potential energy is 0. Okay, now K initial is half mv initial squared plus U initial is mgh initial equals K final, which is half m v final squared. All right, if you factor out m from either side, so if I factor out m from here, I can cancel that with this m, so I have m like that. Then I have half v of I squared plus gi equals half of v final squared. And what are we looking for here? We're looking for this v final. So I have everything else. I have half v of initial squared. We have the velocity of 12 meters per second. So this means 12 to the power of 2 plus g is just 9.81. H of initial is above the building 22 meters high. So I have 22 here. Okay. Then I have half v of final squared. So you can solve this for final velocity. And if you do so, you will find that final velocity squared is 12 to the power of 2, which is 144. So 144 plus 2 times 9.81 times 22. Okay. And then you can write final velocity to be this value under the square root 144 plus 2 times 9.81 times 22. Okay, so whatever it is in the units of meters per second, that would be your final velocity. Now, let's take a look at another part. So what is the answer for part A if the initial velocity is at angle of 53.1 below the horizontal? So in other words, what would be the answer if you're just dropping this down? If this vector for initial velocity, okay, is downward, there is no change. There is no change in the final answer. The only difference is that with this 53.1 degrees above the ground, you will have the path or the projectile taking much longer time to come down. Because we all know when the ball gets to this point, it will have the same v of 12 meters per second at this point, but downward. So there is no change if you are doing that. There is no change if you are aiming this velocity 53.1 degrees down. Okay, now the things that will change is the point that the ball will hit the ground. The point will be much closer if you do so to the building. The time that it will take the projectile to hit the ground will change, but the value of final velocity will be the same. Okay, now part C, if the effect of air resistance are included, will part A or B give the higher speed? So if you are include the non-conservative force like friction, the non-conservative force, the work that this non-conservative force does will reduce your mechanical energy. So and it does depends on the path, okay? So if you're going in a longer path, the friction or the air resistance will do more work. So if you are going in this path, okay, in a longer path, you are killing the energy because the friction is turning that energy to heat by the work that it does, okay? So the final velocity will be less versus if you're aiming this velocity down 53.1 degrees down and hitting the ground, you're going in a shorter path. So you're hitting the ground faster and going in a shorter path, so less energy will be turned to heat by friction. So let's take a look at this example. A piece of fruit falls straight down. As it falls, the gravitational force does positive work on it, and the gravitational potential energy increases, which I don't think so. Let's take a look at B, and the answer is B, if I am not mistaken. The gravitational force does positive work. We know it. Let's take a look to see if it's true. The gravitational potential energy, the work done by gravity is negative mg delta y. Okay, when you are going down, delta y is yf final minus yf initial. When you are going down, yf initial is here, yf final is here, okay? So your delta y is a negative value because initially it's higher and finally it's lower. So this value is a negative value. So if this is negative, then work, because of this negative sign, then work is positive. So then work by the gravity is positive. So it does a positive work. What would happen to the potential energy? Potential energy U is mgh. Okay, h of final is less than h of initial because it's lower, it's dropping, it's falling down. So U of final is less than U of initial. Okay, so the potential energy is decreasing. So if you're looking at this, the gravitational force does positive work, as I just said, and the gravitational potential energy decreases, of course, because it's lowering, it's getting less and less. So finally has less potential energy compared to initial. So rock on the ball. As a rocket slides from point A to point B, along the inside of this frictionless hemispherical, so important part, frictionless, does not have any friction. Okay, hemispherical ball, mechanical energy is conserved. Why? So there's no friction involved. Okay, so we do not have a the friction is not present, is zero. So we do not have so the work done by the non-conservative force is zero. So in other words, the energy is not going to transform to heat because of friction, because the friction is not there. But it says mechanical energy is conserved. Why? And that's the only reason. But when you're looking at the answers, you do not see anything related to friction. We're talking about the normal force here. Remember, I should go back to the beginning of this. One of the non-conservative forces were normal force. So the normal force is a non-conservative force, right? So normal force is a non-conservative force, but it is always perpendicular or with an angle of 90 degrees respect to displacement. So this angle here is 90 degrees. Okay, that's what it is. And the work done by normal force is 0. So even though it is a non-conservative force and exists, but the work done by that normal force is 0. So the work done by normal force is 0 because the cosine of 90 degrees is 0. And that's why. So the normal force acts perpendicular to both surfaces, and that's the reason that it does not do any work. So even though it's a non-conservative, it's not going to kill under energy. It's not going to kill the initial energy, and that initial energy will be transferred all the way to the point from point A to point B. So situation with both gravitational and elastic forces. Elastic forces like what we have, of course, in spring. So when a situation involves both gravitational and elastic forces, the total potential energy is the sum of the gravitational potential energy and elastic potential energy, okay? So U is U of the gravity, mgh, plus the U of the elastic spring, half kx squared, okay? So we know the total work, or sum of all the work done by all the forces, is delta K, or K2 minus K1. Okay. So work done by other forces, whatever other forces we have, like the force applied by somebody, like force F, or any other force, plus work done by gravity, plus work done by elastic forces like spring or something like that, is delta K. But we know the work done by gravity, okay, is negative delta U of gravity. In other words, if I want to write it a little bit better, negative mg delta H, or negative delta U of gravity. We know that. And then the work done by elastic forces is half k x squared, okay, which is negative of delta U of elastic forces. So these two will be equal to negative of delta U. So I can write W of the other forces is delta K plus delta U again, but this delta U is not only from gravity, but also from elastic force, okay, or force by friction. Okay, and if you're looking at here, I have already talked about it. Okay, so if you're looking at this, the work done by spring, or WFC here, or conservative force here, another conservative force, is half kx squared, or UI minus U final, which is negative delta U, as I said before here. Okay, so work here is negative delta U, all right, and the U is half kx squared, negative half kx squared, so negative U of final minus U of initial, and that's what it is. So just keep that in mind. Now, so I am going to solve this for the third part of the video. So this is the end of part 2. I don't want to get the videos too long, so I avoid that. So we're going to solve this problem on the part 3 of the video. If you have any questions for part 2, make sure to comment below, or email me. But otherwise, stay tuned for part 3. We'll go to part 3 right after this.